Unit G, systems of linear equations. Let me explain what a system of linear equations is. A system of linear equations is simply more than one linear equation written on top of each other. Okay? We are going to focus on systems that have two equations. There are things such as systems with 3 equations and 4 and so on and so forth. We're going to focus on 2. There are multiple ways to solve a system. One of which is by graphing, which is what we're going to do today. We can also solve them using substitution, which we'll do tomorrow. And we can also solve them using elimination. It's sometimes called linear combination. We'll learn about that after that. So same types of problems, we're just going to learn multiple ways to solve them. Capiche? Okay. So a linear system, or sometimes it's called a system of linear equations, is 2 or more linear equations that have the same variables. They have to have x and y. The solution to the system of linear equations is all ordered pairs that are solutions to both linear equations. The ordered pair will make each equation true when the values are substituted into the equation, blah, 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 blah. There are 3 kinds of solutions. This is important for you to know. If I have 2 lines and I graph them and they cross at a point, guess what? That point is my answer. That is the solution. Okay? That's one way that the lines could work out. They cross each other, there's a solution. That is the most common way that they end up. Okay? There's also a situation such as this. 2 lines never intersect. What do we call 2 lines that never intersect? Parallel. If they are parallel, we have something called no solution. Because the solution to the system is the point where they cross. So if they don't cross, they don't have a solution. The other one is called infinitely many solutions. And what happens there is the lines, when you graph them, are exactly the same line. In other words, one is directly on top of the other. That means it's touching everywhere. We call that infinitely many. Okay? So? Those are our 3 circumstances. So, first type of problem you will see. Here is the system. And in fact, sometimes you'll see it with a little brace like that. Sometimes you won't. But it's asking, is 2 negative 8 a solution to the system? In other words, is that either the point where they cross or one of the points that's on both of the lines? So obviously wouldn't be this one. So how do I figure that out? Well, I'm going to take this point and I'm going to take both equations. Let me start with the first equation, y equals negative 2x minus 4. The second equation, y equals negative 8x plus 8. If I'm given a pair, aren't I given an x and a y? I need to plug them into both equations, and if it works in both places, it's a solution. If it doesn't work in either one of them, or if it doesn't work in one of them, it's not a solution. The only way it's a solution is if it works in both. So, what am I going to plug in for y? Negative 8 equals negative 2 times, what do I plug in for x? 2 minus 4. So let's see, negative 8, negative 2 times 2, negative 4 minus 4. Negative 8 equals, what's negative 4 minus 4? So it checks out in the first equation. So we're on our way to seeing if it's a solution. If it works out in the next one, it's a solution. If it doesn't work out in the next one, it's not a solution. So, again, what do I plug in for y? Negative 8. And then negative 8x. What am I going to plug in for x? Plus 8. So let's see. Negative 8 equals, negative 8 times 2 is negative 16. What's negative 16 plus 8? So it checks out there. So is it a solution?
Yes.
So my ultimate answer is either yes or no. And the reason why it's yes is because it checks out. Now here's the deal. if I plug it into one equation and it doesn't work, I don't even need to check the other equation. Because the only way it's going to be a yes is if it's true in both places. So as soon as I find somewhere it's not true, that tells me it's not a solution. So I can just stop right there. I don't need to keep going.
How do you know it's not true then?
Say that again?
How do you know if it's not true?
I have a feeling we might find out here. Let's see. So I have two equations. X minus 7y equals negative 34. And negative 3x plus 6y equals negative 6. And I'm plugging in this point. Negative 6, 4. So over here, what am I going to plug in for x? Negative 6 minus 7. What do I plug in for y? 4. Does that equal negative 34? That's what I'm looking for. So negative 6. What's negative 7 times 4? Equals negative 34. What's negative 6 minus 28? So it checks out so far. If it didn't check out, I'm done, right? Because if it doesn't check out there, then my answer is no, it's not a solution. But it does, so I got to go to the second equation. So negative 3 times what? Negative 6 plus 6 times, what do I plug in for y? And I need to see, does that equal negative 6? Well, negative 3 times negative 6 is 18. Positive 18, right? Plus 6 times 4 is 24. Does that equal negative 6? I can tell right now that a positive number plus a positive number is not going to give me a negative. What is 18 plus 24? 42 does not equal negative 6. So guess what? Is it a solution? No. Because if either one of those or if both of them turn out to be not true, then it is not a solution. Questions about that type of problem where you're checking to see if something is a solution? Okay. Now we get into the graphing part. To solve a linear system by graphing, you graph both equations and see where they intersect. You must state the solution. The graph will show the solution, but you must state the point if there's one solution, or you write no solution if they never intersect, or you write infinitely many solutions. So the graph is only half of your answer. Okay? So, example number 1. I'm going to graph them in 2 different colors and see if that helps people see what I'm talking about a little bit better. So, what happened to my pen? Look at that. Do you see that? Looks like the ink went crazy on that. Look at that. It's like covered. We'll see if it'll work for me. Okay. Ugh. Ugh. Okay, we'll see. Hopefully it'll work. That's true. Maybe a red pen is a better option anyways. Okay, so I'm going to graph the first one in purple and the second one in red. Now, the reason why I do it in 2 different colors, you don't have to do it in 2 different colors, is just so that way I know everything that's in purple all is related to the same thing. And then when I'm graphing the red, I can kind of block out the purple because it has nothing to do with the red line. Okay, so in my purple line, what is the slope? You want me to zoom in a little bit? -1. What is the slope? -1. What is the y-intercept?
4.
So what do I start with? Y-intercept of 4 up there. And then what do I do from there? The slope is -1, so I'm going to go down 1, right 1, down 1, right 1, and then I'm going to draw in my line as clearly as I can. Now remember, I need to be thinking that it's continuing that down 1, right 1 process. So I want to think beyond the line that I'm actually drawing. Make sure your line goes to the edges of the grid that I gave you. Any questions about that one? Now I'm going to ignore the purple while I go through the red line. What is the slope of the red line? 4. What is the y-intercept? Interesting, it's the opposite numbers. Totally irrelevant, but that's okay. y-intercept of -1, and then what am I going to do? I'm going to go up 1, 2, 3, 4 over 1. That could be my intersection point, I'm thinking. I can't go up 4 and over 1 again. So I just need to connect those dots. And what situation do we have? Do we have one solution, no solutions, or infinitely many? One solution. They are crossing. What is that solution? This is what has to be stated. What is the point where they're crossing? 1, 3 must be written in parentheses in order to be considered a point. So my answer is made up of not only the graph, sorry I'm off the screen, and the ordered pair. Capiche? That's all we're doing for every single one. Okay? Now, that one was nice because both of those were in graphing form for us. This one does not look like it's going to be quite as nice, does it? So let's see. I'm going to take the first equation, x plus 2y equals 6. And the first thing I'm going to do is get that into y equals mx plus b form so I can graph it. Right? Get y by itself. So what should I do? So I have 2y is equal to what? Negative x plus 6. Then what? Do you see why we practiced this skill before today? So y equals, this would be negative 1/2 x plus what? 3. So what's my slope? Negative 1/2. And my y-intercept is 3. So starting at my y-intercept of 3, I'm going to go where? Down 1, right 2. Down 1, right 2. Again, make sure your line goes all the way to those edges there. All right, the other one, x plus 2y. We'll call this one my red line. X plus 2y equals negative 4. What am I going to do? Subtract x, because again, getting y by itself so I can graph it. So 2y equals negative x minus 4. Now what? Divide by 2. So I get y equals negative 1/2 x, what? Minus 2. What's my slope? Negative 1/2. What's my y-intercept? Negative 2. Right? So negative 2 down here. And then from there I go down 1, right 2. Down 1, right 2. Now what do we have going on there? Parallel lines. How do I know that they're parallel and that they're not just going to intersect somewhere off the graph? They're both going down 1 over 2, down 1 over 2. They're both following that same pattern. Something we'll talk about a lot later is if we have the same slope, we have lines that are parallel. Okay? If we have the same slope and the same y-intercept, we have that going on. But the same slope and different y-intercepts, we have parallel lines. So what do I say? No solution. Now, I just want to be clear. Let's say, here's my fancy little grapher. Here's my fancy little grapher. A little happy grapher guy. Okay, so, isn't he cool? So let's say that I graphed a line, and one of them went, or I graphed a system, let's say, and one of them went like this, and the other one went like this. Are those parallel?
No.
No. But you might be tempted to say no solution because they don't cross, right? They will eventually, so they are not parallel. The problem with this one is I need my graph to be bigger so that I can see where they cross, because it's going to be somewhere over here. So I need a bigger graph for that circumstance. Okay? So if you come across that, you can't say no solution. Okay? All right, you try the last one. Get it into y equals mx plus b form and see what's going on there. Yes.
What would we write on that kind of problem?
On that kind of one, you'd have to draw a bigger graph to find the point. So my goal is to give you a graph that's big enough every time, but if for some reason somewhere you come across a different one, or if you're graphing something online on like Desmos or something, you can move the graph to look over further where it is, and you might need to do it. Okay. One of these is already in graphing form for you. You're welcome.
Wait, there can't be anything attached to a line, not even negative, right?
Say that again?
There can't be anything attached to a line, not even negative.
Correct. So even if you have a negative, you have to divide everything by -1. I'm assuming you were talking about right here. So y equals 3x plus 4. My slope is 3. Y-intercept is 4. That's for my purple line. So that means I start off on my y-axis at 4. Shoot, I can't go up 3 and over 1, can I? So what do? Think about the point that came before. What point did I start at if I went up 3 and over 1 to get to here? Well, that would be down here to go up 3 over 1. And there, correct? Good answer.
Yes.
Ever feel like you're talking to yourself? All the time. Okay, so there's my purple line. My red line is already in slope-intercept form. The slope is 3. Y-intercept is 4. Interesting. Exact same line. So this is a purple and red line. Meaning what? Where do they intersect?
Everywhere.
Everywhere. So we have infinitely many solutions.
If you have the same point, you saw the graph it.
Say that again?
If you have the same point, can you just write how many solutions you saw the graph it?
I should see 2 lines graphed no matter what. It just means that second graph is really easy to graph. Okay, so on your homework, some of them are going to be like these guys where you're checking the points to see, are they solutions? The only way it's a solution is if you have 2 equations and it checks out in both of them. If it doesn't work anywhere, it's not a solution. And you're going to have several of these. I will tell you right now, the majority of your graphs will be like this and will have a point that you need to list. Okay? I'm not going to give you a ton of parallel lines, and I'm not going to give you a ton that have the same. There might be 1 or 2 of those, but count on most of them being like this first example here. Okay? All right, let me pass out your homework. Happy studying.